Swayam Prabha. Digital India. Educated India.
Today we will discuss about chemical Langevin equation. In the previous lectures, we were talking about Langevin equation from the context of Brownian motion, how we can study the dynamics of a Brownian motion, free Brownian particle or a Brownian particle confined to a potential. And then the Langevin equation basically comes out to be a coarse-grained description of the Brownian particle dynamics, and we wrote equations like the acceleration is given by the drag force plus some random force. Okay, so this is a general Langevin equation written for a Brownian particle where the mass time acceleration is equal to the drag force plus some random force. The nature of the random force comes from the interaction between the particle and the solvent molecules. The number of solvent molecules heating the particles are so large, statistically we can describe the force acting on the particle as a Gaussian random variable by this random force. So this is a key element of Langevin equation, which has a deterministic part, and then there is a stochastic or random part. And then we saw a lot of applications: dynamic light scattering, optical tweezers, active particles, and so on. So they're all looking at individual particle and collective particles and their assembly. But the form of this equation inspired application of this methodology to other fields also. One example is chemical kinetics. In chemical kinetics also, one can cast the dynamical evolution of concentration of species in this kind of a form with some deterministic part and some fluctuation parts. Okay, so there's a whole lot of field on chemical Langevin equation. The application involves simple chemical kinetics, and this formulation extended to looking at gene expression studies, and then and from here you can look at many other biochemical networks. Okay, so the chemical species interacting with one another, influencing each other, and the dynamic evolution can also be modeled using chemical Langevin equation. That's why the name chemical comes in here. So we will talk about some examples to start with, and then we will try to make a generalization. Now let's consider a very simple unimolecular decay. Something like some species, chemical species A is reacting with some rate constant K. So when you write a unimolecular reaction like this, immediately you can set up a mass action model or a deterministic model to predict what would be the concentration of A as a function of time. Okay, you will see that the concentration of A will be falling exponentially, something like this. Okay, so this is a deterministic model. Now what we can do is we can actually write the dynamical description of this equation, this model, via a Langevin equation also. So now what we will do is that when I look at this, we will define x of t this as a random variable describing the number of E molecules. and k here is the rate constant. Now for this reaction, we can actually adapt this kind of a formulation and write that dx by dt is equal to minus kx plus square root of kx gamma of t. So if you look at this Langevin equation, and then if you look at this chemical Langevin equation, you can see a lot of similarities. You're looking at the change, the rate of change of some random variable x. Here x means the amount of A molecules present in a reactor. Here V means the velocity of a Brownian particle. So we are looking at how velocity changes here. Here we are talking about how number of molecules of A changes. So here the drag force resists the particle motion. So here this minus kx describes the decay process, A converting into something else. Okay, the minus sign basically means that x is decreasing with the time. In here we encode the solvent molecule interaction with the particle and how that affects the dynamics through a random component. Here we are introducing a similar kind of fluctuation term which goes proportional to the square root of x itself. And why we have square root of kx here is a theorem, is a proof that we will look at it later. Okay, but there is a fluctuating component associated with a Gaussian random noise. Okay, and this number is a random number, and because of this x becomes a random number itself. So you can see a lot of similarities between this and this. The mathematical framework is the same, but the physics is different. So here we are talking about forces acting on particle, various kinds of forces acting on this particle. Here on the other hand, we are talking about what changes the number of molecules through reaction and the fluctuation in that reaction. So in fact, just like how we used to define here, we can also define this. This gamma of t is a Gaussian variable. The mean of this is 0, it vanishes. The correlation function is delta correlated, like before. In other words, we can say that this gamma of t is basically in the limit delta t tending to 0. This is basically the normal random variate with this gamma, the random force that I have here is basically when you take a very small delta t, this is nothing but a unit normal random variable. It's a normal random variable with a 0 mean and 1 by delta t variance. So what one can do is then one can solve this equation numerically or analytically. That will tell you how x as a function of time varies. Okay, so that brings this stochastic nature or the irregularity in the evolution of x. Now what we will do is now that instead of solving this analytically, we look at only the statistical properties, the mean and variance of x through this equation. That's something very similar to what we did here in this case. When we wrote the Langevin equation for the Brownian case, we looked at how the mean and how the variance varied with respect to time. Same thing we can do for this also. So when you apply a mean operation, or when you take an expectation value of x, when I say expectation value, what I mean is that imagine you are actually conducting this experiment very large number of independent experiments. You start with the same conditions, same temperature, same initial number of molecules. The conditions are all the same. So imagine you're conducting this experiment in a very large number of independent reactors, and then the average basically means average over those ensemble of reactions. So here when I apply the averaging operation, you will see that we can write the rate of change of mean is equal to minus k, mean of x. K is constant, okay, because temperature, everything is uniform, rate constant is also uniform. Then you have a correlated mean of x times gamma. Here we say that this Gaussian random noise is an independent, statistically independent random variable. It doesn't depend on what the current value of x is. Okay, so we can separate this out into the product of the means, and we have said that the mean value of the fluctuation is 0. So basically this term vanishes. So basically you end up with a first order equation. Okay, so now we can solve this with some initial condition that at time t equal to 0 is some n, which is a constant. Basically in all the experiment you have started with the same number of molecules to start with. So solving this, you will get x is equal to n e power minus kt. In terms of concentration, you can divide by volume, you will get C is equal to C naught e power minus kt. This is the kind of deterministic result you will get. So what we are trying to show here is that a simple kinetic equation can be written in a Langevin form, and we can show that the mean aspect, the expectation of x basically conforms to the deterministic formulation. Okay, so whatever we are doing in a deterministic pathway, what we are saying is it's about the mean behavior of the system. Okay, now second thing we can do is we can take this and look at what the mean square fluctuation in the random variable x. To see how we get mean square, you can refer to the Langevin description for Brownian equation, how we wrote from the original Langevin equation, how we transform the equation into a mean square description. The same approach can be applied here also. So I am going to give the final expression. You will see that this is 2k x square plus k x. So this equation, when we take the mean square conversion, you will see that the rate of change of mean square is proportional to mean square itself, and also depends on the mean value. And the mean value we already have gotten here as a function of time t. Okay, so we can substitute that here. So this becomes a simple ODE for mean square, variation of mean square x as a function of time. So if you solve this, you're supposed to get something like the following. So you will have an initial condition for this also, x naught square, x square at t equal to 0 will be n square. If you use that initial condition, and then if you solve this analytically, you will get this equation. And here we can write the variance in x . once you get variance in x, what you can find is you can find the ratio of the standard deviation to the mean. This will tell you that how much is the fluctuation with respect to the mean value itself. So the fluctuation may look large, but then with respect to this is called coefficient of variation. It tells you about the mean what is the variance. Okay, if this value is very small, it means that the mean itself is adequate, whereas if this value is very high, basically you are very uncertain about the mean value itself. Okay, so if you see this expression, if you substitute for sigma and if you substitute for the mean, you will see that this coefficient of variation scales as 1 by square root of n, because you've got a square root of n there, n here, you will get 1 over square root of n. So when this n becomes very large, when I say large, I mean thermodynamically large, of the order of moles, 10 power 23 molecules, then you see this number basically goes to 0. That means you cannot really detect any fluctuations. It appears as if it is a deterministic quantity. On the other hand, when n is of the order of, let's say, 1000 or 10,000, then you have this value to be like 1 or 2% of the mean itself. So the system size enhancing the fluctuation is something is captured by this kind of a framework. And this information cannot be provided by the deterministic model that we showed here. Whether I have 1000 molecules or Avogadro number of molecules, this will predict as if the concentration is a deterministic quantity. Okay, whereas when you try to apply this to a smaller number of molecules, the inherent fluctuation will have to show up, and that's what you will see from here. Okay, so what we try to conclude here is the deterministic approach is valid only in the continuum limit, that when you are looking at a very large system size. Whereas now we see a lot of experimental observations are being made in very small number of molecules. A reactor that could be of picoliter volume, or it could be a nanometer sized reactor in which the number of molecules participating in a reaction is far, far lesser. It could be of the order of hundreds or thousands or 10,000s, in which case our way of modeling these kinetics will have to accommodate the fluctuation inherent in the system. And the way you do that is through this kind of a Langevin, chemical Langevin equation. Okay, so that's the kind of the take home message. Because if you look at only this number, it appears as if the fluctuation increases with the n. But you should not look at the absolute value of the variance. You should look at with respect to the mean value itself. Okay, so that's what I was saying. This variance goes as n, or standard deviation goes as square root of n. Okay, so but if you look at the coefficient of variation, that goes as 1 over square root of n. So this number becomes very, very significant for a small system size. Okay, when you look at thousands of molecules. Yes, yes. You can see the mean itself is a function of n. Yes. Yes, we can also find the continuum limit. Yeah. Or to what extent you can ignore the fluctuations. Yeah. You can look at my notes. I'll share the notes. You can see how this transformation was made. Okay. This is a similar approach that we did for Brownian case also. We start with the dV by dt or d and then convert it into mean square. So with this introduction, what I want to really do is I want to make a little bit more generalization. For example, we have large number of species interacting through a large set of network of reactions. How do we set up Langevin equations, and what we can gain from there. This is important because this Langevin equation is a sort of a coarse training. Okay, it is not a continuum limit and not in a molecular limit either. Okay, for example, when you think about chemical reactions, you have to think about the collision between the molecules. And many of these collisions are inert collisions that do not lead to a reaction. So many of the collisions are ineffective. And when you look at certain collisions, they would have enough number of kinetic energy which can be used to overcome the energy barrier, and they will lead to a successful reaction. So that means if you want to look at the reaction in a molecular level, you have to look at an individual molecule's velocity at which they are going, the kinetic energy, and the collision cross sections and so on. And that requires more degrees of freedom to account for. For each and every molecule, I have to know what are their positions, what their momenta, and what the kinetic energy of collisions and so on. So, okay, so that would be the full description of the chemical reaction or chemical dynamics. We are not doing that. On the other hand, we have this deterministic approach where we don't look at any molecular picture, we write a phenomenological equation. Okay, I know that it's a first order reaction. Okay, the rate of decay is proportional to the concentration or proportional to the square of the concentration, so on so. So on one hand we have a phenomenological deterministic approach, on the other hand we have a molecular approach, okay, having all the details of the molecule, momenta, coordinates, and all the other degrees of freedom, the rotational degrees of freedom, the translation degrees of freedom, and so on so. So between these two lies the Langevin dynamics. Okay, so here the Langevin gives you the fluctuation information, okay, which deterministic approach cannot give. On the other hand, it does not include so many degrees of freedom like the molecular picture has. Okay, so how we have done that is through some sort of a transformation or assumption that that one can actually treat the fluctuation in certain quantifiable way. Okay, so that is a crux of this chemical Langevin equation. Towards the end of the lecture, I will also talk about the condition when this approach is valid, and the validity of that is something that is there's no proof to determine. One will have to try and see whether these assumptions are correct or not. Okay, the validity of the assumptions are correct or not. Okay, but notwithstanding that limitation, we can go about and set up this chemical Langevin equation for a more general case. So here in this case, I have talked about only one species reacting. Now I want to extend that to n number of species reacting with m number of reactions. Then you have a state variable. Your random number will become a vector which has the concentration or number of molecules of each species. Okay, your random variable becomes a vector now. So here we talked about a simple single one unimolecular single species reaction. Yeah, so what you do is something called density functional theory or molecular dynamic simulations, where for each molecule you would solve Newtonian mechanics and you will find what the current positions are, what their momenta are, and then look at how many collisions are happening per unit time. Of that, how many are actually reacting to products. Okay, so that would be a computationally exhaustive calculation. Okay, so here we are eliminating all the degrees of freedom by mapping some sort of average rate with which the reaction is happening and then fluctuation about that average rate. Okay, so that's what I meant as coarse graining. So we consider a system that is well stirred or well mixed. That means I am not going to look at any spatial variation, it is a homogeneous well mixed system, and I have species S1, S2 all the way up to Sn. So these are all different chemical species, okay, and they actually undergo chemical reactions R1, R2 all the way up to Rm. So there are m independent reactions and there are n number of independent chemical species, okay, unique chemical species, and they are allowed to react at some certain batch reactor of volume V and temperature T. So this is a problem statement. So we have a vessel of volume V and we have a constant temperature T, and there are n number of molecular species. They are interacting, they are basically reacting with one another through m number of independent reactions. Okay, for example, let's say if I put n equal to 4, I am thinking about molecules like A, B, C, D. Okay, I have got 4 species, and I can think of m is equal to some 3. Then I am talking about 3 reactions. I could have something like A plus B reacting to give 2C plus D, one reaction, and then I have A plus D giving rise to B, another reaction, and then I can write another reaction here that D plus C is giving rise to 2A plus B, something like this. And you can see all of them are actually independent reactions. By multiplying a constant and adding and subtracting, I cannot create one reaction with the other. Okay, these are all independent reactions. So this is what I mean by R1 means this, R2 is this, R3 is so and so. Okay, so now we have 3 reactions involving 4 species. Similarly, here we have n number of molecules interacting through m number of reaction channels or reaction mechanisms. So then what we have is we would like to define X a time t as a random variable, which will have x1, x2 all the way up to xn. Okay, and we call this as a state variable. And each of this x1, x2 all the way to xn, they refer to the number of molecules of xi. This is the number of molecules of Si. Okay, so now our question is, given some initial condition for these species, how can I predict x of t? Okay, so that's a question that we want to ask. Now, this we have only set the problem only partially. What we have not specified is what is the nature of these chemical interactions and how they are going to react. Okay, so for that we need to define what is called the reaction rates. But in this case, we are going to define something called the propensity function. So propensity function is basically a fancy word for rate constants. Okay, so and we would like to also bring in some sort of a stochastic character to this problem. We will say that we'll define a j x of t, this as the probability given that x of t is x, small x, one reaction will occur in the time interval t to t plus dt. So what we are saying is that we are trying to write the interaction, the chemical interaction. We define a variable aj that depends on x of t. X of t is basically the vector. It can depend on the number of molecules of each species. There is a probability that given that the current value at time t is known, what's the probability that one reaction Rj will happen in the time interval t to t plus delta t. Basically we are specifying the rates of the reactions. Now in this case, one way to think about this aj is that you write something like aj as a probability of two things. So the probability of collision and the probability of reaction. Oh, by the way, this is not correct. This should be multiplied by dt. Yeah. So the aj of and times dt, this is the probability. So only aj means the probability per unit time. So if you look at this aj, you can think about physically what it means is, what's the probability that the molecules required for some j reaction, what's the probability they can collide? Okay, because think of, it's a gas phase reaction, the molecules are traveling, so there is a particular probability by which a pair of molecule can collide, pair or maybe other sets of molecules. So there is a particular probability or rate by which the molecules can come together and collide. That is one probability. The other probability is, out of those collisions, how many will actually react. That depends on the energetics of the collision. Okay, so typically this happens to be something like some k naught e power minus e by RT. This is something very familiar to you. This is an Arrhenius law that we write, that this k naught tells you about the probability of collision that depends on the molecular speed, temperature, collision integral, molecular shape, etc., etc. Whereas this exponential term is taking care of the activation energy barrier that tells you the probability of reaction. So we know that the propensity function that we define here is nothing but the rate constant. Okay. Now have we specified all? What we have not specified is that when a reaction Rj happens, how is that reaction going to change the species in the mixture? Okay. For example, if you take this, if this is Rj, I have to also mention the stoichiometry. I have to say if this reaction were to happen, the number of molecules A will go by 1 and B by 1, and it will increase C by 2 and D by 1. So this is called the state change variable. When a reaction happens, we have to say what is the change happening in the state variable. Okay. So that brings us to, we are going to use this new Ji. This is the state change variable. What it says is what happens to the species J when a jth reaction happens. Okay. So if I take this example, or maybe I can take another example, simpler example. Let's say you have x1 plus x2, something like this. Okay, just think about one example. So this if I write, we will call this as R1. So V11 will be plus 1 and nu 12 will be minus 1. So the first index refers to the reaction. So I have fixed the reaction. Then I am looking at the change in the molecule J. So here I have only two kinds of species, x1 and x2. So nu 11 is, by this reaction, one molecule of xn is disappearing, but two molecules is appearing. So the net change is positive 1. For x2, it's just minus 1. Okay, and this is how you have to interpret the state change variable for a given reaction. Okay, suppose if I invert this reaction, I say 2x1 is giving us x1 plus x2. Basically I am saying this reaction is reversible. In this case I call this as a second reaction because these reactions are different. Okay, so I call because it will have a different rate constants. This is A1 and this is A2 and so on. So in this case we will say nu 2 1 and nu 2 2. So when this reaction happens, x1 decreases by 1, so minus 1, and x2 becomes plus 1. So therefore, by specifying two quantities, one is the rate or the propensity function, another one is how each of the rate changes the number of molecules. By combining these two information, we are fully specifying the reaction conditions. We have got n number of molecule species, we got m number of reactions. For each reactions, I am able to specify the propensity function, and for each of those reactions, I am also able to specify the state change variable. Okay, this basically completes the problem definition. Now, what we also do is we'll also split this up into mathematically the following, that Aj is written as some Cj and Hj. So this Cj is more like a rate, and this one tells you how many number of ways the molecules can combine, the number of degenerate states that it has to reach to the same reaction. Okay, so this is more like number of possible ways a reaction can happen, or a number of possible ways the molecules can be chosen. So what that means is, so this should be actually C1. So for these two reactions, we would write that A1 is equal to C1 H1, and C1, the H1 will be nothing but x1 and x2. When I have x1 molecules and x2 second species, the number of combinations of two molecules colliding is x1 times x2. So this is basically the number of degeneracy that we have for this reaction to happen, and this C1 here is the rate constant or the probability per unit time. If you write for this reaction, that would be A2, you would write C2 times n into n minus 1 or x1 into x1 minus 1. This many number of combinations you can have for a binary collision of x. Okay. So the propensity function that we have defined here has two components. One is the rate constant C1 and C2 times multiplied by the number of possibilities, number of ways that this molecule can combine for this particular reaction. Yeah. Yes. Okay, what I am trying to say is that this propensity function we defined there, right? Here we say that this is a probability that RJ molecules, one RJ reaction will happen in the next time interval t to t plus delta t. We are writing this as two parts. One, that is the rate at which it happens per combination and how many combinations are possible. So here, if I have x, so let's say x1 is some 1000 molecules are there and x2 is another 2000 molecules are there. So one x1, one x2 can lead to one reaction. But if you look at all the possible combinations, that is H. Okay, so here you would have 1000 times 1000, that many number of combinations. For every x1 molecule, there are 1000 x2 molecules to collide with, right? So the number of combinations that will lead to reaction, that we write this function H. Okay. So like here I have given an example. If you take this equation, this propensity function you will write as some constant times H1. This H1 is nothing but x1 times x2. If I look at this one, this is a bimolecular reaction of the same species. So the number of possible x1 you will have is maybe you can put a half here, x1 times x1 minus 1, okay, by a factor of half, so that you don't double count. So okay, so for any other given reactions, you should be able to find how many possibilities are there for a given number of x1, x2 and so on and so. Okay, this prefactor is more like a rate constant. Okay, so having defined all this, what we want to do right now is write the chemical Langevin equation for this set of reactions. So we write that rate of change of number of molecules of each species I. This J is a sum over the number of reactions. So this equation basically has this the Langevin character, that we are looking at the rate of change of ith molecule composition species concentration. So you have this kind of deterministic component. So this basically means that ith molecule can be, the ith species can be affected by reactions 1 to m, and this one tells you how ith molecule will change, ith species will change due to jth reaction. Okay, and this tells you this propensity function like we wrote here. So this is more like a deterministic component. Then here comes the fluctuating component or the random component, which is given as sum over all the possible reactions, the state change variable nu ji times square root of ai aj, this is the propensity, and then this is the random variable. For each reaction, jth reaction, we create an independent random variable. Okay, so this is a more generalized form of what I wrote for a unimolecular reaction in the beginning, where we wrote simply dx by dt is equal to something like we had k x minus we had something like kx gamma. We wrote this equation for the unimolecular reaction. Here this minus 1 comes because of this nu, because for every reaction molecule A is disappearing. This x is the h function, okay, h here is just x, and in the square root you have again minus 1 comes out, and then you have square root of kx, and then you have a random variable, okay. So now for a unimolecular reaction like this, you can analytically solve the mean and mean square, but for this kind of a case we won't be able to solve analytically, so you have to adapt some sort of a numerical discretization algorithm like Euler's method and other things. Okay. So, yes. But the number of reactions are finite, right? This is a m number of reactions, and each reactions are, you know, individual and discrete and independent. This is not integral over number of molecules. This is the number of reactions, which is finite. Sometimes we also write this in a different form. We write so this equation and this equation are the same thing, because here we have just defined a capital A, which is nothing but this entire term, and this Bij x of t is basically this entire. So I was talking about you know, the conditions. So basically we would like to mention two conditions when this simplification or coarse graining is possible. On one hand, if you take a particular time interval delta t or dt, and in this time interval you don't want this propensity function to change a lot. You want to maintain the, you want to expect that the propensity function or the rate constants should not change during the time delta t, okay. So that means you are putting a lower limit. If delta t is small enough, then not much change will happen on the rates, so that sets a kind of lower limit. On the other hand, you want to have this delta t be large enough so many reactions can happen, so we can capture the fluctuation as an independent random variable there. So there is some sort of a sweet spot on the time interval that we are looking at, the observation that we are making, that should not be too small and it cannot be too large. If it is too large, then you cannot assume that the propensity functions are constant anymore. If it is too small, you probably don't have enough number of reactions happening, then you have this jump characters of the chemical kinetics. You cannot have this kind of a nice statistically independent fluctuation terms in the equations. So even though it is nice mathematically that you can have a coarse grain approach, where and how to apply is a little bit of a confusing problem. The general approach is that you solve this way and then solve through other more precise methods, which we will talk about later on, chemical master equation, which is more rigorous and more fundamental, and then compare the solutions of Langevin approach and chemical master equation approach, and then we decide whether this approximation for this set of reaction is good or not. Once you do benchmarking, once you know that these assumptions are valid here, then you can do chemical Langevin equation. I also have to tell you, a chemical Langevin equation is far more easier to solve compared to a master equation where the number of independent variables are quite large. So from a computational point of view, if you want to do a quick simulation of a stochastic problem, you should start from Langevin approach. This is the most simplest, most easiest to code. The computational resources needed are also very small. Okay. So with that, I'll stop. In the next class, I will probably talk about the numerical approach to solve these problems.